This is part 12 of the series Applications of Differentiation. In this section, we're going to look at curve sketching. One of the primary applications of differentiation is the determination of the behavior of a function. And there's very few things more powerful than the determination of function behavior than studying the graph of the function. So we're going to look at all the techniques we've learned in pre-calculus mathematics coupled with the stuff we've learned in differential calculus so far in determining how functions behave. And we're going to look at x and y intercepts, where the graph of the function intersects the x-axis and the y-axis. We're going to look at asymptotes, vertical asymptotes, horizontal, slant asymptotes. And we're going to investigate critical numbers. Critical numbers tell us where extrema exist and where other things occur inside the function, minimums, maximums. We're going to look at points of inflection, the points that tell us where the slope of the tangent line is going from increasing to decreasing or decreasing to increasing. And ultimately then concavity, which tell us what intervals the function's tangent line is increasing in slope or decreasing in slope. We're also going to look at end behavior. What is the function doing at its extreme ends, left and right? And the domain and range of a function. Where is the function actually defined? And continuity. Are there any breaks in the function? Are there any values, particular values, which cause issues at specific points inside the function? So let's go ahead and take a look at an example. So here's our first function. It's a rational function, and as you develop more experience and skill with curve sketching techniques, you'll develop your own style and how you like to approach the problems. I like to approach it from an intercept standpoint first because those are usually the easiest to take. So let's go ahead and determine what the x and y intercepts of this function are. So if we set this equal to 0, and we see that the denominator is going to go away, so we have 0 equals 2 times x squared minus 9, and the 2 goes away, so we have 0 equals x squared minus 9. Add the 9, 9 equals x squared, and x is plus or minus 3. So x intercepts is negative 3, 0, and 3, 0. Now let's set the x to 0, and we have 2 times 0 squared minus 9 over 0 squared minus 4. These go away, so we have 2 times negative 18, or 2 times negative 9, which is negative 18, over negative 4, which is 9 halves. So our y-intercept is 0, 9 halves. Okay, now let's go ahead and do our asymptotes. Asymptotes are the thing I like to take care of next. I think they're one of the most descriptive things about a function if the function has asymptotes, and rational functions often do. So the asymptotes of this function are going to be where the denominator is 0. So x squared minus 4 equals 0. X squared equals, x squared equals 4. X is plus or minus 2. So we know that this has vertical asymptotes at x equals negative 2 and x equals 2. And let's take a look at the horizontal asymptotes of this. Horizontal asymptotes, let's take the limit as x approaches infinity of this whole function. And the way I'm going to do this, I'm going to multiply the numerator and denominator, I'm going to divide the numerator and denominator by x squared. So x squared over x squared minus 9 over x squared over x squared over x squared minus 4 over x squared. The reason we did this, of course, is because if we just substitute infinity into x here, we'd have an indeterminate form. So that wouldn't work. So 2 over x squared is 1, and minus 9 over x squared over, this is 1 minus 4 over x squared. When I take that limit, this goes to 0, this goes to 0, and we have 2 times 1 over 1, which is just 2. So we know that our horizontal asymptote is at y equals 2. So let's go ahead and take our first derivative, and let's just rewrite the function down here. So f of x is 2 times x squared minus 9 over x squared minus 4. Give ourselves a little room here, and f prime of x, we'll use the quotient rule. Pull out the 2 first, and we have low x squared minus 4 d high, which is 2x, minus high x squared minus 9 times d low, which is 2x, all over low squared x squared minus 4 squared. Simplify that numerator. We have 2 times, this is 2x to the third minus 8x minus this quantity, 2x to the third minus 18x all over x squared minus 4 squared. And when we simplify this, we see that this 2x to the third minus 2x to the third, those are going to go away. We have negative 8x plus 18x, which is going to give us negative 10x, or positive 10x. So 2 times 10x over x squared minus 4 squared, which gives us 20x over x squared minus 4 squared. So there's our first derivative. Now to find our critical numbers, we would set our first derivative equal to 0. This, by the way, is the first derivative, of course. So we set the first derivative equal to 0. And the denominator goes away, and our x equals 0. So our first critical number is x equals 0. So let's put one of those up here. So x equals 0 is our first critical number. Now let's go ahead and find out where this function has a discontinuity or an asymptote. This first derivative doesn't exist where the denominator is 0, so that's also where our critical numbers are going to be. So we know that x squared minus 4 equals 0, x squared equals 4, so x equals plus or minus 2. And so those are our other critical numbers. So we have another critical number at -2 and 2. So let's go ahead and use those critical numbers to determine, I'm just going to use this space up here. We're going to determine where the minimum and maximum values of this function are. So let's go ahead and draw our line across, and we'll put one test value at -2. I'm sorry, one critical number at -2, 0, and 2. Test value will be -3, -1, 1, 3. So when we evaluate our first derivative at these test values, f prime of x at -3 is negative, -1 is negative. So you can see that this -2 is not a minimum or a maximum. At 1, our first derivative is positive, and at 3, our first derivative is positive. So 2 is neither a minimum or maximum. 0 is in fact a minimum. So we have a minimum value at 0, and if we look, remember that we had a y-intercept at 0, 9/2, so our minimum is our y-intercept of the function. So let's put a minimum at 0, 9/2. So now let's go ahead and determine concavity. So we'll take this first derivative function and we'll take the second derivative of it. So I've gone ahead and rewritten the first derivative. We'll take the second derivative using a combination of the constant multiple rule and the quotient rule. So low times the derivative of the high is derivative of x is 1, minus the high, which is x, times the derivative of the low. This is going to be the chain rule. 2 times the inner function, x squared minus 4, times the derivative of the inner function. Derivative of x squared minus 4 is 2x, all over low squared. Now we just simplify the numerator. Here we have 2x times 2 times x is 4x squared times x squared minus 4. We simplify yet again. We have a common x squared minus 4 in every one of these three terms. So we pull one out here, we have this. Pull this one out, we have the 4x squared. And we pull one of these out, we have x squared minus 4 to the third. Simplifying yet again, we have negative 4x squared plus x squared is negative 3x squared minus 4 all over x squared minus 4 to the third. And we're going to pull out a -1 here. So we have negative 20 times 3x squared plus 4 over x squared minus 4 to the third. Now finally, let's work out our points of inflection and concavity. Our potential points of inflection will occur where this second derivative is either 0 or undefined. We can see that here this quadratic has no real solutions, so it has none where it's 0, and it's undefined at -2 and 2. So our potential points of inflection are -2 and 2. So we evaluate the second derivative at -3, which gives us negative concave down, at 0, which gives us positive concave up, and 3, negative concave down. So concavity does change at -2 and 2, but because -2 and 2 are asymptotes, we have no points of inflection. So there are no points of inflection for this function. Now let's go ahead and put it all together and sketch our graph. Our x-intercepts are -3 and 3. Our y-intercept is 4.5. We have vertical asymptotes at -2 and 2. And y equals 2 is our horizontal asymptote. The function is concave down on -infinity to -2, concave down on 2 to infinity, and concave up between -2 and 2. So now let's practice on another problem.